We now go to the topic of elasticity or elastic properties of materials. In this video, we take a look at the concepts of stress and strain. Most materials are elastic up to a certain point. When we say elastic, when we twist or stretch or compress an object, the object will twist, stretch, or compress. And then when we release the object returns to its original size and shape. So if we deform the object will deform. But if we release the object, if we remove the deforming influence, the object will return to its original size and shape. The material the object is made out of is elastic. For instance, you have a rubber band. If you stretch the rubber band will stretch. But when you release the rubber band will spring back to its original size and shape. Rubber is an elastic material. And most materials are elastic up to a certain point. They may not exhibit elasticity as much as a rubber band, but they still exhibit the characteristic of being elastic. Stress refers to the force per unit area that is deforming the object. The deforming influence, that's stress, and stress is force per unit area, so stress is equal to force that is deforming the object divided by area A. F is applied on area A. A may be cross-section area or surface area. Stress is force spread out on a particular area. And the resulting deformation experienced by the object is referred to as strain. Strain is a measurement of the deformation the object experiences due to stress. And stress and strain are proportional to each other. Stress is proportional to the strain that it produces. And the constant of proportionality between stress and strain is referred to as the modulus or modulus of elasticity. Modulus of elasticity is equal to stress over strain. The unit of modulus and stress are the same. Force per unit area, Newton, meter squared. Unit for modulus and stress is Newton per meter squared. It is given its own unit, Pascal or PA. So stress is Pascal, modulus is Pascal. That means strain, the deformation must be measured in such a way that the strain does not have unit to maintain the equality of the unit. Modulus's unit is Pascal, stress is Pascal, strain must not have a unit so that Pascal equal to Pascal. As mentioned, materials are elastic only up to a certain point. The elasticity of materials are limited. They are only elastic up to a certain point. We have what is referred to as the yield strength or elastic limit of the material. If stress exceeds the yield strength or elastic limit of the material, the deformation experienced by the object becomes permanent. The material is no longer elastic. And if stress exceeds the ultimate strength or breaking stress of the material rips the object, breaks. Depending on how the force is applied, an object will experience different kinds of stress. Depending on how the force is applied on the area upon which it is spread out on. This results in different modulus of elasticity. We have Young's modulus for starters. When the object is stretched or compressed, its length is affected, the object experiences tensile stress. You have an object, cross-section area A, for example, initial length L naught. We apply force to stretch it, force F. To stretch it, the length changes from L naught to final length L. The force applied on area A is perpendicular to the area A. F is perpendicular to A. The object will stretch. The length will change from initial length to final length. The object experiences tensile stress, and the modulus of elasticity for this situation is referred to as Young's modulus or Young's modulus of elasticity. For tensile stress, strain is measured in terms of delta L and L naught such that the equation for Young's modulus, capital Y is equal to stress over strain. Stress is F over A, and strain is measured such that delta L and L naught will give you a quantity does not have any unit, delta L over L naught. Stress over strain, Young's modulus is equal to F over A divided by delta L over L naught. Young's modulus is a property of the material that comprises the object. Each material has its own value of Young's modulus. Next, we have shear modulus, capital G. In Young's modulus, the force was applied on the area A such that force is perpendicular to area A. When the force F is applied parallel to the cross-section area A, you have the object, initial length L naught or height L naught, and we apply force F on the cross-section area A. So area A here and area A here, we apply force F such that F is parallel to the area upon which it is applied. The object experiences angular deformation. From no angle, the material or the object will deform such that you have angle theta, you have angular deformation, we have shearing stress. For shearing stress, shear modulus G is given by stress over strain. Stress, again, is still F over A, force applied on a particular area, divided by angle theta. Theta here is the angle deformation, and it is measured in radians. For very small angle theta, for theta to be very, very small, theta is equal to opposite over adjacent. So if angle theta is small and it is in radians, theta is just equal to opposite over adjacent. So that's delta x divided by L naught. So another equation for shear modulus G is stress over strain F over A divided by delta X over L naught. Just like Young's modulus, shear modulus is also a property of the material that comprises the object. Each material has its own value of shear modulus. And lastly, we have bulk modulus, capital B, when the stress is due to fluid pressure experienced by the object. The whole object itself will either expand or compress depending on the pressure experienced by the object. You have an object, initial volume V naught. Depending on the pressure experienced by the object, that is to say, the deforming influence is applied on the whole surface area of the object. And depending on that influence, whether it is compressing the object or expanding or stretching the object in all directions, the object will either expand or compress. So just for the sake of our discussion, say the pressure is applied such that the deforming influence will compress the whole object. The volume of the object changes. From V naught, it changes to final volume V. The bulk modulus B is given by B is equal to pressure experienced by the object divided by change in volume over initial volume V naught. Stress over strain. The stress is the fluid pressure experienced by the object. And pressure unit is Pascal, just like stress F over A, just like modulus of elasticity, unit is Pascal. So, again, we have stress, strain. Stress is the deforming influence. Strain is the effect of stress. Stress is proportional to the strain that it produces. Modulus is the constant of proportionality. Modulus is equal to stress over strain. Modulus is a property of the material. Since we have three modulus of elasticity to speak of, we have Young's modulus, shear modulus, and bulk modulus. Each material has its own value of the three modulus of elasticity. And that's it for now. In the next video, we'll continue our discussion on the elastic properties of materials. In the next video, we'll take a look at the concept of Hooke's law. So once again, that's it for now. Thank you for watching.